Is that okay? Okay, good. Now, with this Euler planar formula, then we can show K5 cannot be planar. Okay, so let's try. Okay. Okay, so let us add one more condition. So the planar graph is connected and also simple. Okay. Yeah. Well, for this formula to hold, you don't need to have simple. Okay. But we will have a result about simple. Okay. Okay, so first of all, I need to define this term about what is a simple graph. Okay. So a graph is simple if there is no loop, no self-loop, and no multi-edges. So what is a self-loop? So this is a self-loop. So this is a self-loop. So this is a loop. And what is meant by multiple edges? So let's say we have a graph that has 3 vertices. So this is a multiple edges. So if a graph does, so multiple edge means that between 2 vertices there are more than one edge. Then in that case there is multiple edges. Is that okay? So if there is no loop and no, so this is the case with multiple edges. So if a graph is simple, then that means that there is no loop and no multiple edges. Now we have a theorem. Okay. If G is a connected simple, so if it is connected, simple, and then it is also planar graph, then and V, the number of vertices, is at least 3, then we will have the number of edges must be less than or equal to 3 times V minus 6. Okay? Okay, so we are going to show that this theorem is correct. Okay. Now, this theorem is very useful. Okay. The reason is that usually we have a graph and then we don't know whether it is planar or not. If it is planar, of course we can draw it. If it's not planar, then there is no meaning about what is meant by f. Yeah, because it is not planar. So what is meant by the regions? You are not going to draw this on the plane. So in that case, if it is not planar, then is there a way that we can judge it by checking on the E and the V value? If we just need to check on the E and V value and then we can decide whether a graph is planar or not, then it will be a good idea. We don't need to draw it at the beginning. We just show that it is impossible. So here, it gives us a condition, okay, that whenever G is simple and planar, then it can't have a lot of edges. E has to be less than or equal to 3V minus 6. So what is the equivalence meaning? So this is the theorem, right? So what is the contrapositive of this statement? So this is a statement if something then something, right? if P then Q. So it has equivalent meaning as if not Q then not P, right? So what does it mean? It means that if E is greater than 3V minus 6, then the graph cannot be planar. Is that okay? So this is the idea. And this is really the reason that we are showing K5 is not planar. Okay, so let's prove this. So first of all, we are not showing K5 at this point. We are just focusing on a planar graph at the beginning. And why a planar graph has to obey this one. So the idea is simple. Okay, so we are going to rely on this. So this is the proof. We are going to rely on this planar formula. But we have omitted the term f here, right? We have omitted the term f here. So somehow we need to find out how f is related to E and V. So f is a region, right? So this is a region. This is a region. This is another region. This is another region. This is also a region. Okay? Now, to make a region, what is the minimum number of edges that we need to enclose a region? 3. 3. Reason. Yeah, 3, you get a triangle, right? Very good. Why? Why can't it be 2? Can we enclose a region by using just 2 edges? Well, no. Okay, our assumption that the graph is simple. So if you can enclose a region with 2 edges, then that means that there is multiple edges. Is that okay? And at the same time, there is no way to enclose a region with just 1 edge, because in that case, there is a self-loop. So each region must need 3 edges. Is that okay? But you will say, why? Why need 3 edges? Okay, so for instance, you look at the outer space, the outer region. Well, it just have 1 edge. Okay, you just have 1 edge. It's not okay. Well, we rely that V is greater than or equal to 3, so this case doesn't happen. But how about this one? How about this one? It looks like there are just 2 edges, am I correct? Okay. But then what we are going to look at it as, okay, so here we are using this 1, 2, 3, 4 to enclose this region. Is that okay? Let me see if I have another color. We are using this 1, 2, 3 to enclose this part. Is that okay? And then A. Okay, so let's use dotted line. So we are using 1, 2, 3 edges to enclose this part. And you can imagine, somehow, for things to be consistent, we are using 1, 2, 3, 4, 5, 6. These 6 edges to enclose the outer region. Is that okay? So to make things inside out. Can you imagine this? Okay. Okay, so strangely, so these are the 6 edges that enclose the outer space. So these 6 edges is separating the outer space from the inner space. Is that okay? Now in this case, how shall we count? We are going to count this one, and then come back 2, and then this one, and then this one. The reason is that if you look at this case, each edge is counted 2 times. Okay, so each edge, we should count it 2 times. Okay, so in that case, this outer region, we are saying that it is enclosed by 4 edges. If you understand this concept so far, could you please raise your hand? Okay, so in general, we are seeing that each region is enclosed by at least 3 edges. Is that okay? So how many regions are there at the maximum? What is the maximum number of regions we can have? What is the maximum number of regions we can have? The more edge, the more regions we can have, right? Okay, so altogether, we are going to use how many edges to enclose all the regions? We are going to use 2 times of this edge, 2 times of this edge, 2 times, 2 times, 2 times, 2 times, 2 times, 2 times. Actually, using handshaking theorem, we see that the total number of edges to enclose all region is 2e. It's exactly equal to 2e. Is that okay? Can you see this? Okay, so maybe let's look at this as an example. This is easy. So there's region 1, there's region 2, there's region 3, and there's region 4. Is that okay? Now for region 1, we are using 3 edges. Region 2, region 1, region 2, we are also using 3 edges. Region 3, we are using 3 edges. And region 4, we are also using 1, 2, 3, 3 edges. So in this case, total number of edges to enclose all this region is 12 edges. Okay, so this is this case. Now let us take a look of another case here. This is another case. For region 1, it needs 3 edges. Region 2, it has 3. Region 3, how many edges? 1, 2, 3, 4. 4 edges. And region 4, how many edges? 1, 2, 3, 4, 5, 6. 6 edges. So altogether, so this gives the total number of edges is 3, 3, 4, 6 is going to be 16, right? 16 edges. Okay, so how do we get this 16 and how do we get this 12? If you look at it, we count it by 6 here, we count it by 3 here, 3 here, and 4 here. Each edge here is counted 2 times. This edge is counted 2 times. This edge is counted 2 times. Is that okay? So the total value, we don't need to compute. This total value must be equal to 2 times the number of edges. If you're okay with this, could you please raise your hand? Okay, excellent. Now, if you understand this, this is the hardest part to understand. Very hard. Hardest part, okay? But once you understand this, you will see that the number of faces must be less than or equal to, you cannot have many faces, because the total number of edges is just 2e. And then each face will take up 3 edges at least. Some you need 4, some you need 5, some you need 6. But each face you have to have 3 edges already. So you have total number of edges that you can use to enclose the regions, but for each region you take 3 or 4 or 5, at least 3. So we must have f is less than or equal to 2e over 3. Is that okay? Okay? Now if this is the case, then it is easy. So we must have what? E plus 2 is equal to v plus f, and then it is less than or equal to v plus 2e over 3. Now, once you have arrived at this relationship, you have just e plus 2 and v plus 2e over 3. The f is gone. And then you can rearrange the term, and that gets e is less than or equal to 3v minus 6. If you are okay with this, could you please raise your hand? Okay, good. Now, this will immediately show that. So this is, then we have a corollary of this theorem. K5 is not planar. K5 is not planar. Why? Let's count the edges of K5. Let's count the vertices of K5. K5 has 5 vertices, and it has 5 choose 2, which is equal to 10 edges. So 10 is not less than or equal to 15 minus 9. So V is 5 here. So 15 minus 6 is equal to 9. 10 is not less than or equal to 9. So K5 is not okay. If you are okay with what I'm explaining so far, could you please raise your hand? Good. How about K33? How about K33? Can we still use this theorem to show that K33 is not planar? Well, let's try. Okay. Now, so for K33, first of all, it is a simple graph. It is connected, so we want to check if it is planar. So the number of vertices here that we have is 1, 2, 3, 4, 5, 6. There are 6 vertices here. And how many edges here? The edge is how many? There are 9 edges. Is that okay? There are 9 edges. Well, if you plug in the formula, the number of edges 9 is really less than or equal to 3 times 6 minus 6. 3 times 6 minus 6 is equal to 12. So it is really true. So what does it mean? It means that the theorem is not powerful enough to show that this is not planar. Okay, but then we just need a little twist. So we have another theorem. This time, if G is connected simple bipartite planar graph, and let's say, where is my nose? It's gone. Oh, here. And let's say V is greater than and with let me see. Yeah, let me see if I have a formula there. Okay, so I will skip this theorem first. Okay, so let me tell you the idea. Okay, so the proof here is, so with let's say this time V is greater than or equal to 4, then let me see if I have a formula here already. Then we have what? Then we must have F is less than or equal to 2E divided by 4. Does that make sense? Okay, now, so previously we just have simple graph. We don't have a bipartite condition. But now, let's say the graph is now bipartite. Okay, if the graph is bipartite, yeah, you don't need 4. We just need to have 3. Okay. Then if a graph is bipartite, then for each surface, so for each region, because it is bipartite, then what does it mean? So the nodes can be colored in black or white. So this is black, and then we join an edge into white, and then we join an edge into black, and we join an edge into white. Is that okay? Now, if you want to have a region enclosed, then that means what? That means that you need to have even number of edges for each surface. Does that make sense? Yeah, because it is a bipartite graph, and then you want to enclose a region, then you need to go from black to white, white to black, black to white, white to black. And then you want to enclose it, so you need to have even number of edges to enclose each region. You can't have three edges to enclose a region. Because if this is the case, then this is not bipartite. This part already, you cannot color it in using two colors. Is that okay? So if a graph is bipartite, then each surface requires even number of edges. And each surface requires, because it is a simple graph, so each surface must need at least 3 edges. At least 3 edges, and then it is even, so at least 4 edges. Is that okay? So the number of faces must be less than or equal to 2e over 4. Is that okay? And moreover, okay, this is important. Moreover, you must have what? You must have f has to be an integer. So if I say that the number of faces is less than 3.2, then what do you mean? It means that the number of surfaces, the number of faces must be less than or equal to 3. Is that okay? So you must take, you can make it a little bit stronger. Not just 2e over 4, but 2e over 4 taking the floor. You round down to the closest integer. Okay? Now, if f is like this, then let's check K33. Okay, for K33, we have V is equal to 6, E is equal to 9, so that if, so we don't know whether it is true, if it is planar, then f has to be less than or equal to 2e over 4. Has to be less than or equal to 2 times 9 over 4, taking the floor. Okay? So this is equal to 4. So f is less than or equal to this one. So what do we have? So we have e plus 2 is equal to 11. V plus f is less than or equal to 6 plus 4, which is equal to 10. So it means what? It means that V plus f can never be equal to E plus 2. Is that okay? So here we strengthen a little bit. Just by counting each surface, you need to have 4 edges rather than 3 edges. And then by making this stronger, then we will see that the Euler planar formula cannot be satisfied. So in that case, K33 must not be what? Must not be planar. Okay, so this is the case. Okay, so next Monday we will continue. So during this weekend, yeah, try to work on the assignment. Okay, so we will have a tutorial next Wednesday, and then on next Monday we will continue to give you another condition. Okay, this is the strongest condition so far to show that a graph is not planar. Okay, so we will talk about this on Monday. Okay, thanks.